Okay, so what we have here today is an examination of momentum, looking first and exclusively at one-body problems involving momentum and impulse. This comes primarily from section 9.2 in the textbook, but also from 9.4 where impulse is first introduced. The idea here is to use some simple derivations that are only valid for constant forces, but allow us to see the relationship between doing the work-energy equations we've already seen and the impulse-momentum equation that's being introduced in Chapter 9. These are both based on Newton's laws and kinematics, which allows us to have a little bit of an understanding of the way in which we can replace doing problems with Newton's laws and kinematics with equations that involve energy and momentum instead. You should already remember how the work-energy theorem is used. We can calculate the change in kinetic energy of one body if we know what the total work is of all of the forces acting on that body. When interpreting problems, we're generally looking for the fact that we've got a change in speed and we maybe know information about distances and say scalar products of force with that displacement. But we don't know anything about vectors, and we don't need to give a vector answer. And we also don't know anything about time, and we don't need to give an answer involving time. We're only probably interested in solving for a distance or for a speed. So it shouldn't be any surprise that when we do this simple derivation, we're starting from the third of our equations, the one where you eliminate time, and you've got an expression that involves only the speed squared and the dot product, the scalar product of acceleration and displacement. If we multiply this equation by 1/2 m, the left-hand side becomes 1/2 mv squared, which we recognize as the kinetic energy at one point minus the kinetic energy at another point. And the right-hand side, the 2's cancel, and we're left with ma, the net force, times dotted into the displacement delta r. So we have kinetic energy at the second point minus the kinetic energy at the first point equals F net dotted displacement, which is work. If we rewrite this in the way we usually do, which is the second one is final and the first one is initial, and reorder a little bit, we've got K final equals K initial plus the total work. Now that assumes constant forces, which is never really valid in things we deal with in regular problems like springs and other things. The textbook gives a pretty nice derivation based on integral calculus for forces that are restricted to one dimension, that is f of x. And I'd recommend that you read it, especially if you've had Calc 1 and taking Calc 2. But to do the general problem, you really need Calc 3, so I don't really see any point in doing this, especially because those of you in Calc 1 are not going to follow it in any case. Now the other idea is that we have this quantity momentum that changes as a result of something called impulse. That is, the change in momentum of one body is due to the total impulse of all of the forces acting on that body. Again, a one-body problem. On the interpretation side, this means we're looking for things involving vectors, like vector velocity, due to the vector net force, and time. Here, we don't have any distance information. We can learn about time and vectors, but we can't find out any unknown distances. Here we start with the vector equation for velocity. If we multiply through by the mass m, you notice that mv, the momentum, appears in this expression, and ma, the net force, appears in this expression. So this looks like the momentum at time 2 equals the momentum at time 1 equals the constant net force times, not dot product, just times the scalar delta t, the time that elapses between 1 and 2. This last piece is called J, the impulse. The net force is the total impulse J. I've written this again on the next page here so we can say a little bit more about it. The letter J is used for impulse because the letter I is often ambiguously and easily confused with J. So J is often used for quantities that would otherwise have an I in them. There's various places where this is done in physics and engineering both. So that's how you should try to remember the fact that that J is associated with the I. Otherwise it looks completely strange, but that's the way in which it's been done historically. So this quantity J total, notice that it's a vector. In our simplistic derivation, that quantity is equal to the net force, which is a number, but a vector number, times delta t. It has units of force times time, so it's Newton seconds. But it also has the same units of momentum, so it also could be kilogram meters per second. Those are essentially identical units. That impulse is responsible for changing momentum. You can think of it as being a little bit like work, except we've got time instead of distance, and the time is responsible for changing momentum, whereas distance was responsible for changing energy. Again, this assumed the force was constant. Using calculus, we should take into account forces that vary with time, not distance this here, forces that vary with time. The derivation on page 139 of the textbook is really good. I would just suggest you read it. It's easy enough to just walk through here because it's mostly about derivatives. We get two things from this. One is we see the connection to the actual version of Newton's second law that shows up on page 50 of our textbook in equation 4.2, which is written in terms of momentum. And it's then, I think, very easy to see that the impulse equation comes directly from Newton's second law. If we start with the definition of momentum, the vector P for momentum is equal to mv. Take the derivative of both sides, so we get the derivative of momentum on the left. If the mass is constant, that just comes right through the differentiation symbols, and we've got m times dv dt, and of course dv dt is the acceleration. So we've got ma, which is the net force. That means the derivative of momentum is, with respect to time, is equal to the net force vector, and this force vector does not have to be constant. I'll say that again. It's written like it's a constant, but it does not have to be a constant. That force on the right could be a function of time and anything else. The derivative with respect to momentum is equal to that force. Period. That's the general form of Newton's second law. And there are some problems that would be done directly from this law, in particular the rocket problem, which I may have mentioned in class. So now if we look at dp dt equals F, we can do this rather clever trick where it looks like we've cross-multiplied. That is, we've multiplied through by dt to clear the denominator. That's not actually what we've done. There is a version of calculus called infinitesimals where you're allowed to do that, but what you've actually done is just apply a theorem that you'd see somewhere in the area where you do related rates and those sorts of things in your Calc 1 class. This is a really powerful trick, however, a really powerful tool, because now on the left-hand side you see just the differential of p, and it turns out that an integral does the antiderivative process that just turns dp into p. So when we integrate both sides, that left-hand side becomes p evaluated from 1 to 2, from time 1 to time 2. So it's just p2, meaning the momentum at time 2, minus p1, the momentum at time 1. The right-hand side is the integral, that is the area under the function f of t from t1 to t2, and that is what we call j, the impulse. So the impulse is the area under the curve for f of t, that is the integral of f of t dt. It's a vector because f is a vector. If we want to, we can approximate this by an equivalent rectangular area, the average force. This is shown as a nice little graph from the textbook where the rectangular area is f average, the average value of the force, and the width of it is delta t. And the idea is that the area of this rectangle, f average times delta t, is equal to the red shaded area, the orange shaded area underneath the actual force, which can vary quite significantly over the time of some process, like a collision. Okay, so to summarize, we have this equation involving the change in momentum equals the impulse. There's a special case. If the net external force is 0, that means the impulse is 0. The total impulse is 0. If the total impulse is 0, that means the total momentum does not change. And there's a couple of places where this shows up. One is, it's good old Newton's first law. If the net force on a system is 0, the motion is uniform. The momentum, that is m times v, is constant. The speed and the direction of the motion does not change. But you can also have a situation involving two bodies, a collision, where again, the external forces add up to 0. There are internal forces responsible for the collision, but because of Newton's third law, those internal forces cancel out and have no net impulse. As a result, momentum is conserved, that is, the total final momentum is equal to the total initial momentum. And there's a bunch of problems one can solve that way. And there's also a third case which involves the rocket equation in terms of how rockets work when they're in an environment where, again, there's no external force acting on the rocket, and yet it can somehow move. I'm not going to put that in this video. I might put it in a separate one. So this last screen, as usual, summarizes the sources for the various materials.